So our context for today, our story is about Samra's swimming pool. So I think she sounds very lucky because she convinced her parents to build a swimming pool in her backyard. Now the swimming pool holds 2,500 gallons of water. And at the end of the summer, that swimming pool has to be drained. And the pool is going to lose 10% of its water every minute. So we're going to take a few minutes here. Speaking of minutes, I'm going to give you guys about 5 minutes to work through questions 1 through 5. So it tells us in the story that the pool is losing 10% of its water every minute. So what percent of the water is it keeping every minute? 90%. All right, so if we think about all of the water in the pool representing 100%, if we lose 10%, then we have 90% of it left over. So when we're trying to think about how many gallons of water are actually left after 1 minute, there's a couple of ways that we can do this. So if we think about losing 10% every minute, we can think about taking the original amount, so 2,500, and then subtracting 10% of 2,500. So we can easily find a percent of a value if we turn that percent into a decimal and then just multiply that by whatever we're trying to find the percent of. So this is losing 10%. But let's think about what we just talked about in the previous problem, that losing 10% is the same thing as keeping 90%. So wouldn't that be the same thing as just taking 90% of the original amount? Well, with a calculation, 90% as a decimal, we can write that as 0.9 or 0.90. If we take 90% of the original amount, notice how we arrive at exactly the same answer. So we have 2,250 gallons left after the first minute. Well, now we're going to go 1 more minute. And so that means that our percentages now are not based on the original amount. They're based on the ending amount after the first minute. So we're losing 10% from 2,250, or we're keeping 90% of 2,250. The way that those two calculations would look, so it's based on 2,250. The first option is to actually subtract 10% of 2,250 from 2,250, or we could have just done 90% of 2,250. And we should get to the same end result here, 2,025 gallons after the second minute. Now, if we want to try and connect this to an exponential process, which is what we talked about on Friday, the characteristic of it being exponential is that we're continually multiplying by the same number every time x increases by 1. In this case, it would be like every minute, the amount of water continually multiplies by the same thing. And so I think the better option to help us connect to thinking about coming up with an equation here is the second option here of just multiplying it by 0.9. So it's like every minute, the y value, the amount of water, multiplies by 0.9, and that's what makes this an exponential pattern. Okay, so I'm going to think about going from that first starting amount to get to the answer after the first minute, we multiply by 0.9, and then to get to the answer after the second minute, we multiply by 0.9 again. And so it seems to be that the number of times we multiply by 0.9 is the same as however many minutes have passed. And so that can help us with part 4 here, figuring out how to write an equation here. Now for the output, you can use y. If you want to make it a little bit more general, you can also use letters that remind us of what they represent. I'm going to do A for amount of water, but you can also do W for amount of water, or you can just do Y. That's our output. And so what's happening here with our calculation is we began with the 2,500 gallons up here, And we're multiplying by 0.9. And the number of times we multiply by 0.9 is dependent upon how many minutes have passed. And so instead of writing like 2,500 times 0.9 times 0.9 times 0.9 times 0.9 times 0.9, that would be after 5 minutes, because I said 0.9 5 times. We could just say 0.9 raised up to the power of 5. Or in this case, we're going to make it general, and we're just going to have t represent the number of minutes. You could have also put in a little x in there if you just want to use x and y. That's also fine. This is a little different from the equation that we wrote on Friday, where t was representing a time period number of months. So it doesn't always have to be months. You can decide what that time period is. That's going to connect back to the context of your story. All right, so I'm going to just label a few other things here in our equation. So we've got our variables labeled. I'm going to label here, so remember that the position of the 2,500, that is our starting value, or the initial value. So it's kind of similar to when we did Andy's Colt equation on Friday. It has starting weight of 50 kilograms, so we had a 50 in that position at the very start. And then that 0.9 is whatever we continually multiply by. Now we're going to give a slightly different name to this 0.9 in today's equation. On Friday, the number in that position was called the growth factor, but we do not have growth here because if we look at our values, they're getting smaller. And so we talked at the very start of today that today is about exponential decay, and so decay is the word that we're going to use in place of growth. So I'm just going to make a little note here that that 0.9, we give it a new name, and we're going to instead call it the decay factor. All right, so now for part 5, we are wanting to take a look at what the graph of this function would look like and how the graph is similar or different to the graph of Andy's Colt. So I'm just going to bring up Desmos right here on my screen for us to take a look at this together. When I am putting it into Desmos, I'm going to switch it to x and y. So I'm going to say y equals 2,500. Parentheses, we've got a 0.9 up in the parentheses raised up to the power of x. Notice how we're not saying that it's just being multiplied by x. This is not exponential, that's linear. So our x, it's not sitting on the bottom, it is raised up in the position of an exponent. So initially we don't see anything right away. We actually need to zoom out a bit to start to see the graph. I was going to say the curved graph, and the curve is what makes this similar to the graph that we saw for Andy's Colt on Friday. So exponential, we saw these graphs are curved, it's not a straight line, and if we think about what's happening with the number of gallons, this makes sense. We're subtracting a larger amount of gallons earlier on, so these vertical distances are much greater when we go from 1 minute to the next. Well, down here, after it's been like 50 minutes and there's not very much water in the pool left, losing 10% is not losing a huge amount, and so the actual amount being subtracted is getting smaller and smaller. So that's what makes this little curve, and eventually it's going to flatten out. The other interesting thing about this is that if we were to go all the way up, we have relatively small y values here. Compared to the starting amount of 2,500, that is where our line should be crossing the y-axis. So in other words, when t is equal to 0 minutes, the starting amount is like way, way, way up there. It's going to be at 2,500, and then the graph is going to curve outward from that. So the curve makes it similar from Friday's. If I were to actually type in the equation that we had for Andy's Colt, it was 50 times 1.2 raised up to the power of x. Looking at them side by side, we can say, well, what's different about them is that Andy's Colt is increasing, it's growing from left to right, whereas the swimming pool graph is decreasing, It's getting smaller as we go from left to right. All right, so I'm just going to put in a couple of notes about that here, that they both have a curved shape, so that is a way that they are similar. But then the way that the swimming pool one is different is that it's decreasing instead of increasing. And actually, if we were to make a little sketch of the graph off to the side here, this y-intercept point where it crosses would be at the starting amount of 2,500 gallons. And then you see that it's got a curve and then it's just kind of flattening out as it goes further to the right. All right, so moving into the next part here, step 6. It's now asking us to think about, like, what exactly is the relationship between the decay factor and the percent decrease? So for our situation here, our decay factor, that was the 0.9. So that's the actual number in our equation. That's what we're multiplying by every minute. It represents keeping 90% of the previous amount. The percent decrease goes back up here to our story, and it has to do with exactly what it says. The percent decrease, what's the percent that we're losing? In this case, we're losing 10%. So that is what we're going to call our percent decrease. All right, and so what is the connection between the two? Like, what do you notice about how the decay factor, 0.9, how is that related to a percent decrease of losing 10%? Anything you notice? We could write this 0.9 as 0.90. All right, so let's just make a note of that here, that when we have a decay factor of 0.90, our percent decrease was 10%. And so the relationship between them, we can think about them adding up to 100%, or if you turn them both into decimals, they add up to 1. So you can say, like, 0.90 plus 0.10 equals 1, or as percent, keeping 90% corresponds with losing 10%, and that adds up to 100%. So if you have a story and you're told the percent that it's losing, we're just going to subtract that from 100% to figure out the percent that it's keeping. Whatever percent it's keeping goes into your equation. And you can also go the other way around. So if you're looking at an equation and you're trying to write a story, well, the number in the equation is the percent that you're keeping. So let's subtract that from 100 to see the percent that you're losing. So I want to give you a few minutes here to work through the table that you see here for part 7. You're either going to be writing a function to match the story, or you're going to come up with a story for the given function. Now, for all of our stories, when we're dealing with decay, we need to think about percent loss. So, like, we're losing something. And so we had the swimming pool example. Obviously, another one that I put on here is like buying a car, or you can think about maybe like buying a baseball card, and the value depreciates over time. So it's like something that's losing value. I also have the M&M story down here. So I have a bowl of a bunch of M&Ms, and it's decreasing by a certain percent every hour at my birthday party. Another story that I like to think about is I have an overweight cat. So I put him on a diet, and he's losing a certain percent of his weight like every week. So you can kind of get creative with the stories here and thinking about something being lost. But you're also welcome to use one of the templates of my story that I have up here, or even the one that I just mentioned, and just replace the numbers with what they should be instead. Awesome. All right, so really the big thing is that the percent that we're describing in our story plus the percent that corresponds with our decay factor in our equation, they're always going to add up to 100%. Okay, let's go ahead and turn over to the back side of our paper. We have been talking mainly about decay here on the front side, and on the back, we are going to get a little comparison here, side by side, between growth and decay. So this is going to help us with our first learning target of how do we identify what kind of situation a function is modeling. So there's a lot of things that are similar in the way that exponential growth and decay works. So if we look at this description, first off to the side, the description here is exactly the same. So in order to get the new amount, we're going to take the previous amount, we're going to call it the old amount, and we're going to multiply it by a certain value called b. And we're going to continually multiply by that same number. And that b shows up right here in the equation. It is the number that's holding up the exponent. The only difference here between growth and decay is that growth is when b is some number that's greater than 1. So if you continually multiply by something bigger than 1, it's going to grow. The end result is going to increase. Now for decay, the number that we continually multiply by is something less than 1. It still needs to be greater than 0, but think about something like what we had today. Think about like a decimal number. You could even do this as a fraction. I think with our stories, though, it's more common that you'll see it with a decimal. Some number less than 1. So if we continually multiply by something less than 1, the end result is going to get smaller and smaller. I know it seems weird to think about, like, how could you multiply and get an answer that's smaller? Well, it depends on what you're multiplying by. So when we multiply by 0.9, at the beginning of today, we saw that that answer was smaller than what we started with. All right, and then the setup for our equations here looks really similar. We talked about this general form on Friday, so it's a times b to the x. A just represents the starting value, or the starting amount, and this is actually going to show up as the y-intercept on the graph. And so when we do a comparison between our two graphs, so whatever that starting amount is, A would be here for growth. It has a curve, but it's increasing as we go from left to right. For decay, this is like what we saw on the swimming pool graph on Desmos. The y-intercept starting value is at the top, and then it's actually decreasing as we go from left to right, but it does still have that curve in the shape. All right, so thinking about doing a comparison, thinking about growth and decay at the same time, the next table that we are going to be filling in has these different situations mixed together. So we have some that have growth and some are decay, and determining if it's growth or decay is part of what we're going to be filling in the table. All right, so we're going to take a look at these first two functions together. So first off, our starting value. That should be easy to find. It's going to be the number out in the very front. Now, when we take a look at this number here that's holding up our exponent, because 1.07 is bigger than 1, so this situation represents growth. So 1.07 from our equation, that is the growth factor. And that's going to correspond with a percent increase of 7%. So remember from Friday, if we are going from a growth factor to a percent increase, this is where we need to subtract 1 or ignore the 1, and then turn that resulting decimal into a percent. Just looking at, like, what's the percent increase amount that's happening on the end of the 1. All right, let's take a look here at the next one. So this one has a starting value of 48. And it looks like we're continually multiplying by 0.15, which is a value that's less than 1, and so that means that this is going to be decay. The decay factor is the exact number that we have in the equation, so that is 0.15. And so what we have in the equation, like that's always the amount that we're keeping. So here we're keeping 15%. So to get our percent decrease, we need to think about what we're losing. So if we subtract 15% from 100%, we're losing 85%. So this is just what we talked about today, that 15% and that 85% are going to add up to 100%. When you're filling out this side of the table, make sure that you use the words increase or decrease, and that it's going to match with however we answered it being growth or decay. All right, so we have a soccer ball that's being dropped from a height of 4 feet, and it's giving us information about how high it is rebounding after each bounce. And so at the starting height of 4 feet, we can convert that into inches. We'll call that 48 inches. And after one bounce, it says that it's at 19 inches. After 2 bounces, it is at 7.5 inches. Well, if we were to do some division here, so if we do 19 divided by 48, we see that it's multiplied by this value here. If you do 7.5 divided by 19, we're multiplying by this value right there. Notice how they're not exactly the same, but they're both pretty close to about, let's say this is approximately 0.395. Looks like that's what our multiplier would be. So we can do that with a division to help us kind of figure out an estimate of what it's continually multiplying by. So our starting amount here is 48. That's what we're multiplying by. If we want to estimate the height on its fifth bounce, we're just going to plug in 5 in place of x and just put that into our formula.